best software library for modeling and simulation of solar desalination systems. www.redslibrary.com.
Hi everybody, Professor Mohammed Shah with you. Today we are going to talk about solar photovoltaics for reverse osmosis desalination plants, the concepts, and how can we run our model by the use of Red's library. Okay, the main concept is solar photovoltaic power reverse osmosis desalination plants can provide easily fresh water to remote communities that don't have sufficient natural source of fresh water. Remote communities are often located in areas with access to seawater or brackish water or groundwater and so on. For such communities, maybe small scale of reverse osmosis can provide fresh water. Even for large scale, photovoltaic can serve such technique of desalination. Add to this, we can add some energy recovery devices such as fuel cell unit, wind turbine, battery banks, because the desalination technique is more sensitive to the energy consumption. It needs sufficient energy in order to work under stability operation. Reverse osmosis is a water purification technology that uses semi-permeable membrane to remove ions, molecules, and larger particles from drinking water. It's quite applicable for drinking water purification, some industrial processes, military uses, food industry, hydrogen production, and so on. The main concept of our work is to provide photovoltaic array to overcome the load by the high pressure pump. High pressure pump is the heart of such system because it's a responsibility to produce high pressure in order to force saline water to be extracted as a brine and fresh. So it may consume a lot of power. So photovoltaic it can serve in such case. We have three main configurations for reverse osmosis. We have basic module without energy recovery devices. We have a peel-to-wheel device. We have pressure exchanger device. This is a basic module, which is a feed water stream goes through the high pressure pump and then split it into rejected stream and fresh water stream. This is a basic one. This is the second configuration. It's about using the high pressure from the rejected brine in order to drive on the peel-to-wheel turbine in order to give a recovery power to the high pressure pump, to reduce the load on the high pressure pump. This is quite interesting and very good configuration. The third one is the most efficient one, is to split the feed. Split the feed means also it will decrease the pressure, the load on the high pressure pump. So we are going to split the feed and exchange the pressure of this stream feed with the high pressure from the rejected brine, because it's waste brine. So we are going to utilize its pressure to transfer its pressure and exchange with the feed, and proceed it again and to the mixer unit. By this operation, we are going to reduce the load on the high pressure pump. For our model run, we are going to discover the following: the load on what is the load on high pressure pump in such in case of using basic or peel-to-wheel turbine or pressure exchanger. What is the design aspects of reverse osmosis? What is the feed stream? What is the needed feed stream? What is the brine rejected stream? Some irreversibilities and so on. What is the PV photovoltaic design aspects like the needed area, because the investor or designer need to discover I'm going to produce some amount of fresh water. So what is the total area of the system that should I utilize in order to produce such amount of fresh water? What is the unit product cost? It is quite important to know what is the unit product cost of the whole system. Okay, for our system, we have to go to our destination folder and run our model from here. The model should appear like this. Okay, as you can see, on the main model we can watch some tutorials. Okay, this is our plant. Okay, we have three main units: reverse osmosis plant, okay, photovoltaic system, and splitter and control room unit. For reverse osmosis, we can discover the following. What is the configuration we are going to deal with? Some operating conditions, some design, membrane type according to the target productivity, the performance of the pumps on turbine, some aspects related to built-to-be turbine, and the same for pressure exchanger. For photovoltaic system, we have to choose between watt per meter square module or kilowatt hour per meter square. Okay. Suppose we are going to deal with watt per meter square. Okay. For control room, we have cost aspects, interest rates, membrane costs, specific chemical costs, treatment, and replacement cost of. I will keep this stage. Okay. Let's try a simple model. Okay. For let's repeat to turbine. Okay. Suppose I'm going to, this is ambient temperature, operating conditions, seawater temperature. Suppose it's around maybe 17. Let's change everything. Seawater salinity, let's keep it at 38,000 ppm. Productivity, I'm going to choose 3,000 or 1,500. Little bit larger plant, medium size plant. Okay, meter cube per day. Okay, for this, for seawater, I'm going to choose membrane type seawater, 30 high recovery. Okay, and number of pressure vessels. I think for such technique, I am going to choose 40 with 7 elements per pressure vessels. High pressure pump 85, recovery ratio 30-35. It's okay. Fouling factor, okay. Yes, for turbine we have to select, we have to assign outlet pressure, kilopascal, and built-to-be turbine efficiency, and the rest is for pressure exchanger. Okay, choosing watt per meter square model. Okay, let's go for watt per meter square model. Okay, I'm going to select operating hours. It's okay, 24 hours. Yes, I'm going to select 500 watt per meter square, maybe in winter. It's depends on your location, sure. Or you can download our solar data model, and you can connect solar data model and change this parameter. Sorry, in order to sure, you can input your location, longitude, latitude, something like this. Design, I am going for 280 watt module type. Battery performance cost, I keep such parameters as it is. Okay, let's go for built-to-wind turbine model. Let's hit run. Okay, as you can see here, we have this is total area, specific power consumption, pressure. It's around 46 bar. Let's think decrease the number of pressure vessels. I think it's 20 in order to emphasize the pressure. Okay, and let's see now. Let's hit run. Yes, it's increased. That's quite good. This is okay. High pressure. Yes, this is high pressure pump power. Okay. This is built-to-wind turbine power. It's around 150 kilowatt. Okay, we're going to subtract this value. Okay, subtract this value here. I think it's yes, from here. Okay, and this is the final value of the this is the load on photovoltaic. It's around 330 kilowatt load on photovoltaic, and this is feed flow rate, brine flow rate, salinity, reversibility, product salinity, and so on. Okay, let's change such change some parameters. Okay, for photo, yes, let's discover what is going on here. Okay, for 300 kilowatt we need 1136 number of modules with cell area 377 centimeters square. Module area is 3 meter. The total system area is around 4,200 meters square. Battery storage, number of batteries, costs, and yes, here membrane cost, annual replacement, annual fixed charge, mechanical labor. Okay, annual PV cost. Yes, this is unit product cost. We have to watch this parameter because this is this can reflect the total cost of batteries, reverse osmosis, chemicals, photovoltaics, and so on. It just shows that we are going to sell our product by $0.64 per meter square, US dollar per meter square. Okay, let's go dynamic. I mean let's change some parameters. Set our time into infinity. Okay. Okay, let's watch this. Suppose I'm going to change. Let's hit run first. Okay, let's change productivity and watch the pressure. Productivity, I'm going to increase. Okay, therefore the pressure is increasing up to 8. Therefore I have to increase the number of pressure vessels in order to stabilizing the pressure not exceeding 80 bars or lower than 40 bars. Okay, so increasing. And what's specific bar consumption? Increasing the plant productivity would increase specific bar consumption, and this is effect sure on the total area of the photovoltaic system. Let's see here. This is the total system area. I'm keeping increasing Okay, increasing productivity, therefore increasing the power of the high pressure pump, therefore increasing the load on photovoltaics. Therefore I'm going to increase number of pressure vessel. I will reduce the total area again. Okay, what about increasing controlling some parameter in yes, this photovoltaic system? Let's control solar radiation. Suppose I'm going to control solar radiation. Increasing solar radiation would decrease the solar system, the total system area, as you can see here. At midday, I'm going for midday. Okay, no, it's decreasing. Okay, let's stop. Now we are going to see some curves. Okay, for this run, I think this is, yes, this fluctuation of the specific power consumption, because we are going to increase and decrease, increasing productivity, increasing at the same time increasing the number of pressure vessels. So this fluctuation is the same was happened with the pressure, and the pressure has the maximum effect on a specific power consumption. Let's see reversibility, exchange of feed, exchange of the brine. Okay, let's see pressure, fluctuation of the pressure. Yes, nearly the same. Okay, this is let's watch the power here. Power. This is the power. Mass flow rate of the feed, brine flow rate. Okay, what about photovoltaic system? I think we have number of modules. Yes, this number of modules. Yes, and let's see here. There's number of modules. Okay, I'm going to add. I need to add. Okay, number of modules here. Okay, this is solar radiation, increasing solar radiation. Okay, total system area, I think this one. Yes, this one. Module area. Yes, module area is decreased because we increase solar radiation. Okay, total system area, sure, fluctuating because of the effect of feed, then effect of the pressure vessels, and then effect of solar radiation. Increasing would decrease, and so on. Okay, we have a simple system. It's quite interesting. We can study a lot of design aspects. We have to control the productivity, some operating condition parameters, and watch the game from this. What is the total area? What is the module area? What is design aspects for the reverse osmosis plant? It is quite interesting to explore for the designer and the investors. What is the future of, if I am going to desalinate about 1,500 1 meter cube per day, and so on? We have to watch. I forget to. Yes, we have to watch this parameter. Okay. Let's see the effect of this parameter. It's quite interesting. Let's see. Hit run. Yes. Okay, for yes, changing this one. Let's change the productivity, decrease productivity. Yes, we can decrease the productivity and decrease sure number of pressure vessels. I'm going to decrease more and more. Yes, decreasing pressure vessels mean increasing the total pressure on high pressure pump. Therefore, the specific pump consumption is trying to increase or rise up. Therefore, this number will increase. Okay, again, decreasing number of pressure vessels will increase the cost. Okay. Okay. Therefore, we have to decrease to the total blend productivity. I'm going for 3,500. Let's get down to 40s. Okay, 40s. Yes. Stop. Okay, I think it's quite interesting to study such configuration for the designers and so on. I'm sure you can draw your system. I think we are here for Turbine turbine. Yes, this is one. There's two runs, the old run and the new run. As you can see the difference. Okay, and here Exergy. You have many parameters to address. I think it's quite easy to run such a model. The model is simple, quite interesting, durable, and so on. Okay, don't forget to download power cycle for reverse osmosis, thermal power cycles, geothermal power cycles, Rankine cycles, fuel cell with reverse osmosis from redcyber.com. Thank you for watching. Thank you very much. Don't forget to like, share, and subscribe. Thank you very much.